Okay. So, I didn't really have a whole lot of questions from the book this week. I mostly wanted to spend time going over the program, if anything. So we'll probably just go over. I want to do set-associativity and then maybe Hamming codes, and then we'll just jump into that. Oh yeah, and make sure to post in chat for attendance, as always. Oh no, it's not letting me move it. Everything's ruined. Oh, it worked for a second. There we go. Okay, so the first one is 5.11. So we have a set-associative cache has a block size of 4 16-bit words and a set size of 2. The cache can accommodate a total of 4,096 words. The main memory size that's cacheable is 64 kilobytes times 32 bits. Design the cache structure and show how the processor's addresses are implemented. Okay, so I wanted to just briefly show how we would allocate all this space, and then just maybe do one example of how a set-associative cache works, and how the tag bit is actually calculated. Again, for the program, I don't recommend, and I know Dr. Fonseca recommended this too, try not to do the set-associative, unless you want to, go for it. A direct memory addressing is way easier to implement. Actually, not that much easier, it's just one less step, really, but I definitely recommend direct memory addressing. So we'll say RAM is over here. And then we got cache. And then, like the book does, I'm just going to separate from now on the tag bits from... Oh, this is question 5.11. I'm going to separate the tag bits from the cache itself. So recall that the cache has lines, and each of those lines, even though their name is a line, is actually just a block of memory from main memory. It's just copied over. So, let's look back over to this really quick. We have a set-associative cache has a block size of 4 16-bit words. Okay, so we're just going to assume maybe that each word addressable is 16 bits, and a set size of 2. So the cache can accommodate a total of 4,096 words. So this one is, they just throw a bunch of numbers at you, but let's work it through really quick. So we want a block to be 4 words. So the 16-bit part doesn't really come into play for the first part here. We want 4 words per block. And we know that the cache can accommodate 4,096 words. So the blocks in cache then, we're just going to take the 4,096 words that it can accommodate, and we know we're dividing it into blocks, blocks of 4 words. So divide by 4, and that should be 1024. So the cache then is going to have, block here, I'm going to erase it in a second. It's going to have 1,024 blocks. We have 0, 1, ... 1023, 1024. That's probably a little hard to read. (1023, 1024). Okay. Cool. And then if we apply the same thing to RAM, so let's figure out how many blocks that has. So main memory size that is cacheable is 64 kilobytes, or 64K times 32 bits, which I think is a strange way to put it. But if we think about it, 4 16-bit words, that means that a block is, in other words, so a block in this case is 64 bits. So that means that if we took the 64K times 32 bits and divided that by 64, then we know the 64s are going to cancel. So we're going to get 32K blocks bits per block. So 32K blocks. Won't the highest go up to be 1020? Oh yeah, sorry, you're right, because I started counting at 0. Thank you. $10.23. Thank you for that. Yeah, and then this one is going to be 32K blocks, which is 32 times 10. Oops, not 10. Is there a way you can increase the thickness of your pen tool? Yeah, let me click that. Times 2 to the 10th. Hopefully that's better. Yeah, my pen is actually broken, so sorry about that. Hopefully it doesn't just draw all over the screen. Yeah, let me at least outline like the important parts. So there's 1024 cache. Oops, that's a bit rough. Cache blocks, and then in cache. Oh yeah, there it goes. 0, 1, ... 1022, 1023. These are the tags, and then yeah. Okay. So we have a lot of blocks in RAM here. 2, ... and then it ends at 32 times 2 to the 10th. Let's just say big number at the very bottom. So there's a lot more RAM than there is cache blocks, right? Which I guess is what we expect. So now we need to consider the fact that we want to split this into sets, since we're doing set associative. So if we were just doing direct memory access, remember that all we would have to do is take each of these block numbers and then just modulus it by whatever is over here, and then it just ends up in the cache, right? We just directly map each block to one block of memory to one block of cache. But in a set associative, we're going to map each block to a set and then do stuff within that set. So, yeah. So what we're going to do is, instead of doing blocks, we know that there's 1024, right? We know that we want each set to be 2 blocks. So how many sets are there going to be if we have 1024 blocks, and we know that each set is going to contain 2 blocks? 1024 blocks. 512. Yeah. Right, exactly. So we're just going to take those 1024 blocks and split those into 2 blocks per set. And like people in the chat are saying, 512 sets then. So what I'm going to do is basically group each of these together into groups of 2. So instead of blocks, maybe let's just change this a little bit. So we're going to have set 0, set 1, and then set 2, set 3 until we get to set 512. And then this was obviously block 1. And then we'll say the set is in blue. And the last would be 511. Yeah. Again, it would really help if I could count. That'd be good. Thank you. So 511. And I'll get this one right. 1022, 1023 for the block. Does that make sense so far? Is that the sets are just groups of blocks, but we partition it the same way we would normally do it. For direct memory access. Okay, and then we'll just maybe look at the tag bits. So the way this works, and I just wanted to go into more depth on this. For both direct and memory, or direct and set-associative, the way we come up with the tag and the block that it actually belongs into, in this case the set rather than the block, is we want to look at the value itself, and we want to hash it into this cache. And the way we do that is just with the modulus operator, which is a really easy way to do hashing. So in this case, we're going to take whatever the memory is, and we're just going to modulus it by the cache size, which in this case is 1024. So for instance, if I wanted to take block 2, I don't have a lot of room. I'll maybe do another quick example off to the side on the next one, just with a smaller cache, because this one's kind of big too. What we do is we simply take whatever the block is that we want to copy, so we get some sort of operation in the actual CPU, right, where it has a opcode and an operand or some memory address. We figure out that we need to move the memory into cache because we got a cache miss. So when we go to populate it, right, we would take whatever the memory block is. So let's just say we take 2 here. Oh no. Yeah, my pen is a little busted. Let's try to fix that. Alright, there we go. We want to take 2. Then we know we would just take 2 mod 1024, which is equal to 2. So this stuff here gets copied into set2, which I didn't draw. So let's just say instead, just so I can actually show it in the picture, we have block number 1024 down here, and then there's more memory. So if I was to take this one, actually let's make it a different number. Let's make it 2048. ... Okay, so if I want to put block 2048 from main memory into the cache, I need to figure out what set it belongs to, which is 2048 minus the cache size, right? We say the memory address minus this cache size, and that is 0, because 2048 divided by 1024 is 2 remainder 0, so it's going to end up in set 0. Okay. And then the advantage of set-associative, so if you noticed, the problem with direct mapping is it's very easy, it's super fast, but the problem with direct mapping is that, and somebody pointed this out last week, is that a lot of these values are going to map to the same block. So like 1024, 0, 2048, 4096, all 4 or 3, how many ever I just said, are going to map all to block 0 in direct mapping. But in this case, they're just going to map to set 0, which has 2 blocks inside of it. So if I was to access memory address 0 and then memory address 2048, I can put both of them in set 0 without having to go to main memory every time I want one of those two and like overwrite the previous one. So we get a lot less collisions in this case when we use a set versus when we use a direct address. So what's going to happen is we'll just populate the first block of set 0 with the contents of 2048. Now, let's just say, man. Alright, there we go. Let's just say I wanted to access memory address 0 now. I would do the same thing, right? I would take 0 modulus 1024. I would get that it belongs in set 0. And now I don't have to overwrite this value. I can just put it in the same set. Does that make sense, though? That we base what set it goes into based off of what this is modulus the cache size, and then we can just put it wherever. So the disadvantage of set-associative, and associative as well, is that we spend a lot more time searching than dynamic. So dynamic, direct mapping. We map it directly to one block, which we can just go to and look at. But here we have to go to the set and then figure out where it actually is, and then whatever the tag would get set, and I'll go over an example of that in a second. And the search for whenever we would go and look for the memory, so let's just say for whatever reason I try to access memory address 0 again, and for the sake of the tag, just know this isn't realistic. Oh my god, it's like the worst day for this to break. I'm just going to put the full memory address, but we're going to see in a second that's not actually how that works. If I was to go and access memory address 0 again, I would have to look through this entire set in order to find if it's in there before I know it's a cache hit or a miss. So that's the disadvantage of set associative, is that even though we hash to a set, we still have to do a linear search and just check, is this one 0? Is this one 0? Until we find it. So no. Yes. Yeah, I'll move chat over a little bit. Like a binary search. Or it's like a linear search. You just go straight down in a line. There is, and then you exit when you find it, obviously, but there's I think it's called the content addressable memory unit. I don't remember the full name. There's like a piece of hardware that's good at finding this. It just does it in one cycle, I think, or maybe even two. It just like ANDs and XORs, I think. I was looking at the architecture the other day, but I know it's optimized to actually do the linear search. Oh, he did? Okay, sweet. Okay. Any questions on that? I'm just going to do one quick other example of this. Seems like there's no. Okay. So let's just go here. So again, let me do an easier example, because I think those ones, the numbers are too big for me to do it easily. It does seem inefficient to check all the cache for every memory retrieval. Yeah, right? So that's why we split it into sets. The advantage of set associative over associative is that we do a hash first and then we do the linear search, rather than just jump straight into the linear search and then go through the whole cache, which would be really terrible, honestly. Okay. So we'll have the cache over here with the tag, and then we'll have main memory. So what I'm going to do, if my pen would click, that'd be great. Okay, what we're going to do is partition this into blocks. So let's just say there's some arbitrary block size. Let's not worry about the numbers too much. Six ... So let's just say RAM has at least 6 blocks, and that's just all we'll deal with for now. So I'm just going to write some of these out in binary. So as a byte. So this would be 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. This one would be 0, 0, 0, 0, 0, 0, 0, 1. And then we'll just skip down a bit. So let's see, I was planning on doing this. So 0B, 0B. So 4 in binary is 0. Oh my god. I might just have to write with the mouse at this point. 0, 0, 0, 0. 4 would be 8, 4, 2, 1. So 0, 1, 0, 0. And then 5 would be 0, 0, 0, 0, 0, 1, 0, 1. Why are these 8 bits long? Just because I want to fit it on screen. In reality, it would probably be 64 bits. But I just want to do it for the sake of being able to see it. Okay. And then let's just make the cache 4 big. And then again, I'm going to do these in binary. So this one would be 0, 0, 0, 1, 1, 0, 1, 1. And I'm only going to do 2 bits here. The reason because there's only 4, and that's all the bits I need to represent these, right? And you'll see why that pays off in a second, hopefully. I might even throw an extra thing down at the bottom here. Okay. So I was saying earlier that the way we were doing tags where we just store the entire memory address, that's not efficient. And I do recommend you to do it that way for the sake of your program, just because, you know, that's easier to do. But that's inefficient when we're designing an actual machine. So what we're going to do instead is, and I'm going to, let's just say this is direct memory for the sake of doing it. But know that Set-Associative works the same way for splitting this. So I want to put memory address 0 into the cache. So where is memory address 0? Which block is it going to go to? Right? Yep. It's going to go to block 0, right? Because 0 mod 4 is 0. So what I would do is I would go to cache and I would put it in there, whatever is in the memory block, and then I don't need to store this whole address. So I've been doing that this whole time, but that's not realistic. And we'll see if we notice a pattern. So let's say I go and I do memory address 1. Which block is that one going to go into? 1, right? Let's put that in there. So let's just say the cache blocks for these. This one's 0, 1. What about 4? Which one is that one going to go to? 0, right? And then what about 5? It's going to be 1, right? Oh, yeah. Did you have a question? Oh, you just said 1. Okay, I got it. Right, so these are going to keep going in patterns, right? It's going to be 0, 1, 2, 3, 0, 1, 2, 3, over and over again. So let's take a look at what these share in common. So we said these two go to 0, these two go to 1. Do you notice anything in common between the things that go to the same cache block in terms of their binary representation?
The first 7 bits?
Right, or not the first 7 bits. And actually, I'm being a little misleading with it. But somebody's saying the least significant bit, and yeah, and actually even better, the last 2 bits. So you're right, the last bit is correct, although I was a bit misleading with this. But if you notice, everything that maps to the same address has the last 2 significant bits. And actually, it's actually not 3 in this one, because this one is different from that one. But if I was to keep going, this is like 0, 0, 0, 0, 0, 0, 1, 0, and 6 is 0B, 0, 0, 0, 0, 4, 2, yeah, there we go. So it'll be 1, 1, 0. And you'll notice that even if I do it for 2, right, these are the same there. So we actually know everything that hashes to the same thing is going to have the same last 2 bits. And the reason it's 2 here has to do with the size of the cache. The size of the cache is 4, and the reason I wrote these earlier is the fact that the number of bits required to represent 4 numbers is 2 bits. So that's why the 2 bits here correspond to actually the block that we know it needs to go to. So if I had a size of 8 for the cache, how many bits would I need to check to tell which block it actually goes into? 3, right? And so if I had 16, I would need 4, and 32, I would need 5, and so on. So, you know, if you're mathematically inclined, you need log base 2 of the cache blocks, number of bits, and the least significant bits, like somebody said, in order to figure out what cache block or set, if we're doing set associative, it goes into. So when we store the tag, we only need to store the rest of the address. So for the tag for 0, I wouldn't store the whole 0, I would just store 3, 4, 5, 6 bits. And for 1, I would store, again, same 0, 0, 0. For 5, I would store 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 5, 0 in memory. Is that clear? I just wanted to make sure everybody knew that in case you decide to implement it. Any questions on that before I move to the next one? It doesn't seem like it. So let's just go over one last one. Right, which was Hamming codes. Oh yeah, so they say for the Hamming code in figure 6.10, which I have here. Okay. So a Hamming code is just a way to check for errors. And I'm going to do it the same way they do it with this numbering system. So what we do with Hamming code. So let's just say for the example here, we have a piece of data that's 8 bits. So these D1, D2, D3, D4, D5, D6, D7, D8, that's the input. So we're getting some input data, and it is just arbitrarily chosen to be a byte. And just to follow up with what they have, I'm going to say it is 0, 0, 1, 1, 1, 0, 0, 1. Is that right? 0, 0, 1, 1, skip 1, 0, 0, 1. Yeah, that looks correct. So let's say that's our input data. What we're going to do is we're going to generate a Hamming code. And if you remember from class, the way we do a Hamming code is we take the original data, and at every point that there is a what's it called? A power of 2. So we're not going to index it at 0 just for the sake of making this easy. Every time there's a power of 2, we're going to throw in what's called a check bit, and that's basically just to check later if we had corruption in this data from either hardware or sending it over a network or something like that. So what I'm going to do is I'm going to take the input data, and at every power of 2, I'm going to throw in a check bit. So what I'm going to do is, this is position 1, So I'm going to throw in the first check bit. The next position would be position 2, which is also a power of 2, so I'm going to throw in another check bit. And then I keep going. So the next position is 3. And what I'm going to do is I'm just going to start copying these over. So 1, position 4 now is a power of 2. So we'll just put a check bit there. And then position 5 is... I should probably make more space. Position 5 is not a power of 2, so I just copy it from the original word. And actually, let's just say I wanted to allocate this in advance. The number of check bits I'm going to need is always going to be the floor of the log base 2 of whatever the input was. Floor? 3? I guess it's the ceiling. Or it's probably the floor plus 1. 10, 11, 12. But I should have... Basically, I should keep going, making every one of these power of 2 bits into a check bit. And every other position is... Oops. From the actual original input word. So if you notice here, I have 4 check bits, just because when I'm throwing this in, I want to make sure I have space for all 8 of the original bits here. And so there's 1, 2, 3, 4, 5, 6, 7... Did I skip one? 1, 2, 3, 4, 5, 6, 7, 8. No, I just can't count. So I need to make sure there's 8 there and then just room to accommodate the check bits. So if I just copy that over, this is the 1 from there, 0, 0, 1, 1, 1, 0, 0. So you notice in green that is the original input word, and then I'm just going to throw in some check bits there. Does that make sense so far, or any questions on what I just did? Makes sense so far? So far so good? Okay, fair enough. And if you have questions, just interrupt me. Okay, so now what I'm going to do is generate the actual correct Hamming code. So the way we do that is... You'll notice that the book has like a Venn diagram. I don't think that's a great way to do it. We'll look at things that are multiples of that check bit. So again, 0, 0, 1, 1. I'll leave a space. 1, 0, 0, space 1, and then 2 check bits. So if I want to check bit 1, what I'm going to do is look at everything that is 1 away. So I'm going to take, and when I put D, I just mean data bit versus a check bit. So I'm going to take data bit 3, and I'm just going to XOR all of these together. And I know the book does it a slightly different way, but you'll notice this works out to be the same. So I'm going to just skip every other one. So I'm going to check this, that. Basically all the odd ones for the first one. So I'm going to do data bit 3, data bit 5, data bit 7, data bit 9, and data bit 11. Which in this case is 1 XOR, oops, that's a little big, XOR 0, XOR 1, XOR 1, XOR 0. Okay, let me make that a little more clear. No, it broke. Oh my god. Alright, it's going to work eventually. 1, 0, 0, 1, 0. And what does that all XOR to? Anybody tell me? And this is why it's called a parity bit in the book. Yeah, somebody says 1. Yep. You guys are right. That's a 1. And just as a reminder for everybody, XOR just means if they match, you get a 1. If they don't match, you get a 0. And so we could do this one by one, but the shortcut to that is to just count the parity, even or odd, of 1s. So in this case, we have 3 1s, 2 zeros. Zeros don't really matter. We have 3 1s, which means that it is a even parity, and so we go with 1 because 1, or sorry, did I say even parity? Odd parity, because 1 is also an odd parity. So the check bit 1 is 1. And you'll notice that matches what they have too, right? They say it's 1. Okay. What about check bit 2? And I'm not going to draw all these all the way out. Whereas we did every 1, like blocks of 1. For 2, we're going to do blocks of 2. So I'm going to look at these 2. And then I'm going to skip 2, and then these 2, and then skip 2, and then these 2, and then skip 2, and then there's not enough to keep going. So in this case, I'm going to have check bit 2 is equal to data bit 3. It's not B. Data 3 XOR. Okay, and then we skip 2, so 4 and 5, and then we go to the next 2, which is 6 and 7. D6 XOR D7 XOR, and then we skip another 2, so we skip 8 and 9, and we do 10 and 11. Does that pattern make sense to everybody? And we're going to keep going. If we were to do the other check bits, we're going to keep going with that pattern. So can anybody tell me what check bit 2 is going to be then? If I XOR all of these together, and maybe it's a little easier to read their thing. XOR 1, 0, 1, 1, 0. One. Yep, exactly. So if I count these in these blocks of 2, then I'm going to get 1, 2, 3 ones, which is, again, an odd number. So it's going to be 1. Oops. Actually, I should probably do this in red, huh? As if they all match. Well, not if they all match, but if it's an even number of matches, rather. Okay, so I think that's a little bit easier to see. So let's just do check bit 4 really quick. So check bit 4, I'm going to do the same pattern. I'm going to go in blocks of 4 now, though. So I'm going to do 1, 2, 3, 4, skip 1, 2, 3, 4, and then look at the last 4. So in this case, I have 0, 0, 0, 1, and 0, which is, again, it looks like 1, right? Yeah, if we double check there, they have 1 as well. So we get an even number again. And then if we do 8, we're going to do 1, 2, 3, 4, 5, 6, 7, 8. We don't actually have 8 bits, but we count 8 and then keep going. And you'll notice here, what is check bit 8 going to be if I count these 8 bits to the left of it, which is actually only 5. But there's going to be 2 1s, which is an even number of 1s, so that check bit ends up being a 0. Does anybody have any questions on how I got those check bits? And just consider, I know it might be hard to tell with my drawing, but when you count those 4, 8, 2, or 1, you include the check bit in that count. So here I counted 2, 1, and then skipped the 2. Can you go over the pattern for data bits when solving C2 again? Yeah. So if my pen would work. So for C2, I'll go down for this one. So for any of these, I want to look at whatever the power is that that check bit represents. So for C2, the power it represented would be 2, right? I want to go... Actually, let me do it on their thing really quick. If I wanted to find check bit 2, if I want to do check bit 2, I would have to look at multiples of 2. So for check bit 2, I would want to check position 2, 3, skip 2, position 6, 7, skip 2. Whoops. So I did make a mistake there. Oops, there we go. Skip 2, these 2, skip 2, those 2, skip 2, until I've covered the entire word that I have. Does that make sense? So if you notice, like the data bits here, we would get 2, which is actually the check bit itself, so I'm not including it, and then data bit 3, data bits 6 and 7, and data bits 10 and 11. Yeah, I can do C4. So if I did C4, it would be these ones. And then I skip 1, 2, 3, 4, and then I do the next 4, but there's not actually 4, so I only do just the one that would be part of the 4. And then I guess I'll just do C1 as well, just to complete it. So for 1, I would do 1, skip 1, 1, skip 1, 1, skip 1, 1, skip 1, 1, skip 1. And then I would keep going until I run out of stuff. Any questions on that? What would C8 be? So C8 would be this, and then we do 8. So I would go, just make a different shape. 1, 2, 3, 4, 5, 6, 7, 8. So we would go until we hit 8 bits, which we don't actually have. So it would just be all of them in this case. So again, that's how I'm getting these. I'm just looking at all these 1s and 0s that fit into those categories, and then XORing them together to get the check bit. Okay. If you had more bits, you would skip 8, right? Yep. So if I had like 30 bits, I would go until I hit 8 bits and then skip 8 and then do another 8 until I just run out of bits, because you just might not have a input size of data that fits perfectly with power of 2. And in fact, you really shouldn't get one because most input data is going to be a power of 2 anyways. So check bits are in powers of 2, so every word can be checked evenly. Yes, kind of, yeah. So it's make sure that we cover, you'll notice here with the drawing I did, it covers every single bit. Every single bit is included in one of my calculations. And you'll also notice that the only time a check bit is covered is when it's in its own box, right? Check 4, that bit is only in the red box. Check 2 is only in a blue. Check 1 is only in a green. Everything ends up skipping over them, which means that we don't end up checking a check bit within a check bit, because that'd be kind of bad. When what we're trying to figure out is the data corrupt? We don't really care about these check bits. They're just there to tell if the data is corrupt or help us with that. Okay. So I'm just going to open a new tab really quick, and we're just going to go with what we had. So again, if we look at the original word, so it says word stored as, we had it as zero, zero, 1, 1, 1, 0, 0, 1, and then again, I'm just going to highlight the check bits. So check bit 8 is 0, and the rest were 1s, right? 1, 1. So we get 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1. Yeah, that matches up with what they have. Okay. So let's just say we store this in memory, and alpha particles are just shooting out of the sun at unhealthy rates, and it comes and then it hits data bit. So in their example, I thought it was data bit 6. Maybe I'm wrong. Data bit 3? Yeah. I might even do it a little differently than them. Let's just say it comes and hits data bit 6. So this is 1, 2, 3, 4, 5, 6. Or no, it is data bit. Yeah, it is. Yeah, let's just say it comes down here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have some sort of radiation, and it comes in and messes up our computer. And so this bit flips, but everything else is fine. So that bit is now corrupt. What we want to do is recalculate the check bits. So if I figure out what this bit string should be, then let's take a look. So again, what we receive now is 0, 0, 1, 0, and then the check bit 8, and then 1, 0, 0, check bit 4, 1, check bit 2, check bit 0. Okay, so we just copy over what we know will be the data bits and what we know will be the check bits, because we know even if there's a corruption, they should still be in the same position, right? And then we'll just recalculate the check bits. And I said 1, or 0, I meant 1, check bit 1. Okay, so if we do check bit 1 again, then we know it will be every other one. So we get 1, 2, 3 ones, right? 1. So that's even. And then for check bit 2, we check every other 2, starting at the second position. So we do this. Skip 2, 1, 2. These 2, skip 2, those 2. So we get 1, 2, 3. Oh yeah, assuming we skip this. Oh, did I even count that right earlier? 1, 2, 3. No, I'm sorry. Check bit 1 would have been a 0. Yeah. Check bit 2 would be a 1, 2, 3 would be a 1. Does that make sense? Because I'm not including the check bit itself. So 1 would be this one, and that one. Wait. Did I count that wrong again? No, they're 2. 1, 2, right there. Which is a even parity, so there's 0. So just to, again, write this off to the side. Check bit 1 would be equal to... Oh my gosh, my pen. Check bit 1 would be equal to... Oh, you know, let's just do it on this thing again. Check bit 1 would be this one, that one, that one, that one. This one, which is the one that I actually changed in mine. So this is I changed this to a 0, right? And then I didn't change data bit 3. This one is the same. So is that clear now that the check bit, there's 2 1s that aren't the check bit, so it should be 0. And then check bit 2 would be these 2, skip 2, these 2, skip 2, these 2. And then if we count how many there are 1, 2, 3 in this case, which means that it's even parity, so it would be a 1. Or sorry, odd parity, which means it's a 1. Or 1 is odd, 0 is even, because 0 is an even number and 1 is an odd number. Also, that's just the way XOR works. and then check bit 4. Again, we would go groups of 4, 1, 2, 3, 4, skip 1, 2, 3, 4, check these. And in this one, there is 1, which means that's going to be a 1, it looks like. I don't think that makes sense. No. 1, 2, 3, 4. We end up at position 9. 6. Check for bit 4 should be a 0. What did I do wrong? Am I just counting wrong? I think I just copied that down wrong. No, check bit 4 is a 1. It was originally a 1. Yeah, sorry, I'm looking at that wrong. Because this is check bit 4, right? Yeah, that's correct. Oh my god. All right. And then check bit 8. Again, we do the same sort of pattern. We do the same sort of pattern, so we do 8 at a time. And for check bit 8, there's only 1, 1, which means that it's even. Okay. So this is the data with check bits that we get from the original input. And just consider this was check 1, check 2, check 4, 5, 6, 7, 8, check 8. So these are the ones that we ended up basically not overwriting, but that ended up changed when we calculate the actual check bits that should be there, that we expect to be there for the data that we had. Does the process make sense, at least, on how I generate the check bits? I would just do it again with only checking the data bits and then recalculate the check bits once I get it again. Right, because we know it's corrupt, and we can actually figure out exactly where the corruption is. So let's just do that really quick. Fetch. So what we fetched originally was 0, 0. Again, I'll do this in red. 0, 0, 1, 0. We know this one was the corrupt bit, right, earlier. Okay. 0, 0, 1, 0. We fetched a 0 for check bit 8 originally. And then it was 1, 0, 0. And then originally we fetched a 1 for check bit 4. And then originally we fetched a 1 and a 1 for check bit 2 and check bit 1. So this was the original bit string that we fetched from memory that was corrupt. And then the generated one, when we recalculate the check bits, was 0, 0, 1, 0. So all the data bits will be the same. We didn't actually update those when we did the calculation. All we found were check bits, right? The only thing that's confusing is using XOR. Okay. Yeah, I'll explain that in a moment, because we do need that for the... Actually, yeah, I'll explain it after I write the string. Because we do need that for the program as well. 0, 0, 0. So that you'll notice the data bits are the same. The check bits are the only thing we recalculated, which is 1, 1, 1, 0. So what I'm going to do is I'm going to XOR these two strings together. So just to answer your question, XOR, the truth table for that, so if I have A XOR, if my pen would work, A XOR B. and I do the truth table. So this is binary. There's two operands, A, B, and then let's just say the result out. So the possible inputs I could have would be 0, 0, 0, 1, 1, 0, 1, 1. Those are all the inputs for two combinations, right? The truth table for XOR is 0, 1, 1, 0. The way to think of it is if they match, it's 0, so it's false. If they're the same, or sorry, if they don't match, they're not the same, so 0 and 1, 1 and 0, then we get a 1 out. And that's what XOR is, just by itself. The shortcut to doing XOR is to look at how many 1s you have. So if I had 1 XOR 1 XOR 0 XOR 0 XOR 1, that's 1. 1 XOR 1 XOR 0 XOR 0 XOR 0 is 0. Is to count how many 1s do I have. If I have an even number, like this here, or this one here, then we're going to get a 0 out. This one has 0 1s, which is an even number, and this one has 2 1s, which is an even number. So every time I see that pattern, it's just going to reduce down to the same exact thing. Whereas if I have an odd number of 1s in my XOR, it's going to equal to 1. So that's why we call it a parity bit, is if you XOR a bunch of things together and you have an even number, then it's always going to be a 0, and if you, which is also an even number, and if you XOR an odd number of 1s, then you're going to get a 1, which is an odd number. So XOR, you can kind of shortcut it to mean is what's the parity of this string? Is it 0 or 1? Or even or odd? Same thing. Does that answer your question for what XOR does? Instead of 1 0 1 1 at the end of the corrupt fetch, isn't it 1 1 1 1? 1 1 1 1. Yeah, you're right. Sorry, I messed up. For C1, we have 3 1s, but we got 0 check bit. 1, 2, 1, 2. It's position 5, 9. We should get a 0, but what did I mess up? Oh no, it should be 0. No, the check bit itself isn't included because we're recalculating it. We're assuming, so that can be a little bit confusing. And I know they do it in the book too, and it's a little tricky. We exclude the check bit from the calculation. In fact, I think they do the check bit and then they flip the XOR, but that seemed more counterintuitive to me. We check everything that's not the check bit, and then we generate a string with the correct check bits from the data bits, which we don't calculate using the check bits itself normally anyways. Yeah, I know that could be a little bit confusing. But is that clear? This should be the correct string that I generated. Is it clear how I got that? The fact that the original one was fetched corrupted, and then this new one I used the corrupted data to try to... yeah, and if you get the check bit, if you include the check bit, you're going to get the exact opposite. And that's what they do in the book. So you'll see that they do that. Just know that you're supposed to flip the answer if you do that, because, yeah, they did it including the check bit. So, like I was saying, this is the last thing we'll do. We get out what's called, I think they use this term in the book too, but I know Dr. Fontes loves to talk about this if you take a class with him. This is a syndrome, which is just, what do I get when I XOR all these? So 0 and 0 is a 0, 0 and 0 is a 0, 1, 1 is a 0, 0, 0 is a 0. So all the data bits, we expect to get zeros out. Now if we look at this check bit, the check bit that we got from the corrupted data was a 0, which was originally generated from here. But when we regenerated the data bit, we got a 1. Those are a mismatch. which means that this is a 1. Let me just do all these other ones really quick. So all the data bits, we expect when we do the fetch versus the generated one, because we didn't change them, the XOR is always going to be 0 because they're always going to match. But on the check bits, it might be a 0 or 1. So here we see there's a mismatch, but on check bit 4, we see that there is a match, so that's a 0. On check bit 2, we get the same thing. There's a match, so it's a 0. And check bit 1 is a mismatch, which is a 1. So we get a syndrome of this bit string right here. Now, what we were saying earlier, somebody pointed out, is if the syndrome is not all zeros, then we know that the data is corrupted. And the reason that the syndrome is helpful is it tells us where the corruption happened. So what is this in binary? What is that in decimal? Well, this is the number 1, 2, 4, 8, 16, 32, 64. Whoa. Okay, I'm sorry. Looking at the check bit. This is position 1, this is position 8. I'm sorry. I'm going a little overboard. The two that we noticed were wrong were position 1 and position 8. What position was our corruption in? If I look up here, it was position 9. That's 1 plus 8. This addition is proving really hard with a broken pen. It's like the hardest part of the class. 1 plus 8 is really difficult. I'm just going to do it with my mouse. It's alright. 1 plus 8 is a really big 9. Quick maths. Very slow maths because my pen is broken. But that's the cool thing about a syndrome, is it tells you exactly where the data went wrong. So let's just consider 2 last things with that, and then we'll spend the rest of the time doing homework. The program, which I was hoping to have more time for, but oh well. If we look back really quick, the original question was, for the Hamming code shown here, what happens when a check bit rather than a data bit is an error? So what happens is that since this is an addition, right, and we know that we only put the data bits in powers of 2, that means that if a check bit is incorrect, what's going to happen is only that check bit is going to be marked in the syndrome. Because if I wanted to, let's just say, have check bit 8 be corrupted, 8 in binary is 8 plus nothing else. So only position 8 would be a 1 in my syndrome. Which means, just in general, yeah, that was the other thing I was going to bring up. If there's 2 check bits corrupt, then you kind of get a double flip, and I think there's other methods to actually test for corruption like that. The chances of it happening are very unlikely, so that's why this is still reliable. But yeah, you bring up a good point. If there's 2 or more check bits corrupted, this actually doesn't work as far as I know. But it's so rare to have that happen. It's rare enough to have a bit flip anyways, that we usually just say this is good enough. But yeah, I guess what I was saying with the other one is that we'll only have 1 position marked if it's a check bit, which means if you you figure out in your syndrome that you only have 1 bit marked, then you know for sure it had to have been a check bit. Because any other thing that's not a power of 2 has to be a sum of 2 or more powers of 2. And that's the answer to their question. So if you only get 1, then you know I don't even have to do any data correction, because, well, it was not corrupt. But if I get 2 or more, then it definitely was corrupt. And again, it only corrects 1 bit. 2 or more bits, it shouldn't work. Okay. So now, unless anybody had any questions on that, I think we'll just move on to talking about the homework. So, let me just open a few things. I'm going to try to go through this as quickly as possible, and if you need extra time, feel free to stay and ask stuff. So I sent a zip file in the Discord, and I encourage you all to download it, because it includes stuff to help with the IAS emulator. So what I've given you is a memory generator, which this just generates a file of integers that you can use to initialize your RAM in your program. So you can read this data in and store it in your RAM, and that way you have RAM that's consistent. You don't have to do it yourself. And on top of that, you can use my sample programs, and you can tell, using that given RAM state, that you can run every single time and have the same RAM. Well, did my program run correctly from the RAM? So there's that. Memory init.ex, or space ex, is just a generated RAM file. So I suggest using this one rather than using the memory generator.py. Just copy this file. So it's just RAM. It goes all the way down to 2 to the power of 24, and it's just all integers that you can use to read in. I think I accidentally put a line feed at the bottom, but just skip that, I guess. Why not init RAM to 0? Well, then all your math is just going to be like 0 times 0 plus 0, and yeah, that's probably not too interesting. Can I open the Python file? Sure. I mean, it's really simple. You can look at it in your own time. I sent it. Do we load it? Yeah. So that's what I would suggest. You either initialize it yourself, but the problem with that is that you're probably going to have to do a random generator, and then every single time you run, you're going to get a different RAM state. So that's why I recommend using my thing. Why do you subtract 5 from the bit power in the for loop? Because an integer is 32 bits, and 32 is 2 to the 5th, so I need to make it 5 less to accommodate for the fact that an integer is that many. I'm not going to focus on this too much. You can look at it in your own time. Yeah, read the memory file into your RAM array. That's the reason I wrote it, is so that you can do that, because that way you always have the same memory every single time you run your program, and that way you don't have to sit there and look in a debugger at all of your memory and be like, yeah, I think this makes sense. Just use my memory, because I've already written it in a way that you know what the answer is. Yeah, I hope that clears that up. So just initialize your RAM to everything from this memory init.ex, or memory init.ex. You can generate your own with the memory generator, but I don't suggest it. Opcode Enums is really simple. If you're using C++, just throw this at the header of your file. It will set load equal to 1, store equal to 33. So you have constants that you can use when writing your switch statement. That way it's easier to read. So you could do like case print, case add, case subtract, and it will just figure out that's the number if you do the preprocessor directive. The README just explains all this. So I've written programs that are very simple, and you'll notice that the IAS is like basically unreadable. So this is not going to tell you much. So I've written what it means in actual stuff. So I have like 3 programs: adding.ias, math.ias, and self.ias, and they're really simple. So in my memory state, so I've written what these actual programs do here. Let's zoom in a little bit. So adding.ias, the opcode, or the assembly for it that I wrote was load from memory address 9, add memory address 15, add memory address 19, store in memory address 300, and then I put in an extra opcode into the stuff just for the sake of your debugging that I encourage you to do, but you don't have to if you have like a debugger and you really just want to scroll through stuff, I guess. But I think it's just easier for both me and you if you write a print, because it's just write C out memory 300 and we're solid. It's much easier for me and for you, I would hope. Yeah, so I have this here. Load from memory address 9, add memory address 15, add memory address 19, store in memory address 300, print address 300. And what I've done is I've just converted these to hex. So the opcode for load is hex 1, the opcode for add is hex 5. You'll notice it's the same twice because they're both add. Store is 21. Print I just arbitrarily picked to be 4. That's different from the actual IS machine, so I just threw that out there. And then these all match up with the actual operand, right? 9 is 9, 15 is hex F, 19 is hex 13, 300 is hex 12C. And I hope I converted all these right. I tried to do it using a program, so hope that's right. And so if you use my memory init ex, you'll expect this answer to be 6 plus 10 plus 20. So memory address 9 is the number 6. Memory address 15 is the number 10, and memory address 19 is the number 20. So I just picked those memory addresses randomly to give small numbers so you can have an idea of what to add. So there's a 6, 10, and 20. So just remember that you're fetching the contents of that memory address, not 15 or 19 itself. And then I just arbitrarily picked 300. And so I wrote 2 other programs that are very similar. They're super simple. And I give a description of what they do here for all of them, assuming you use my memory allocation or my memory initialization file. This is all what you expect to get, what it actually does, assembly, and opcode. And then just to explain these are all just the integers if I was to take these hex values and convert them into decimal. That way you can natively support it. If you're doing C++, you can just like read it in using cin and it's fine. So that's why I did that. Because if I did it in binary or hex, I would have to ask you guys to parse it, figure out what those actually mean in binary or hex, and then assign it to a integer, and then you could do a byte array, I guess, but I don't know. That seems difficult. I mean, if you decide you want to do it that way, just copy and paste all this stuff, or turn it into binary if you really want to. I don't expect you guys to parse something that's like a little bit extra. I think parsing binary wouldn't be bad, but that's too much work, and I get a huge file if I do that. So I just didn't want to force you guys to do that. I see. So this computer can't really handle literals. No, I can't. And nothing should be able to handle literals. What actually happens, you don't write this in assembly usually, because the assembler and the compiler, vice versa, or both, should take any literals you're writing and actually just load them to a memory address and then replace where you put the literal with the memory address, is what it should do when you actually write the machine code from a compiler or an assembler. See, because the CPU doesn't know what a literal is, as far as it's concerned. So no literals. Any questions on any of the stuff I wrote? So Opcode Enums has every opcode we have to implement. Yeah. And in fact, it has 3 extra ones that you don't have to implement, but I put there for later because he seemed to imply that you're going to do them. Mention that the instructions did not utilize the MQ, so we won't have to implement that. You can if you want to, but you're going to have to rewrite my instructions if you do. I just figured it would be easier just to have an accumulator and just not force you guys to do an MQ. Yeah. I didn't want to make it harder than it had to be. But if you want to do MQ, by all means, just change. You'd have to add in the extra, like, load and store MQ opcode. Is the IAS computer programmed to read from these IAS? No, I just put IAS. I just felt like it. These are just text files. I just put IAS so you know. Any other questions regarding this stuff? If not, I'm just gonna... So can you go over interrupt implementation? Yeah, did he want that in this version? I can do it. Next version? Okay. Yeah, I'll talk about it if anybody doesn't have any other... Oh, it's too soon? Okay, maybe I'll still do it. I guess that's what the load and the store IO that I gave you would be for anyways. Okay. I think on Wednesday next week. Fair. Okay, yeah, so let me think about how I would do that in a high-level language. So, yeah. what I would do... I was thinking writing a recursive function for an interrupt. No, I'll just put an if statement. Handle interrupt. Yeah, or a function. That's fine too. Just one function. But just one if statement, I think is fine. And that's probably a good idea. Just make a handle interrupt. Let's do that actually. Does it say we have to handle interrupts? Not in phase 1. From what people are saying in chat, it's phase 2 that you need to have interrupts. Sorry, I haven't had time to look at anything on the website this week. I've just been programming a lot, so. But yeah, apparently it's due next week. So, what I would do is I would mimic the structure of what I drew in that one example last week, where we had an interrupt register, hypothetically, an interrupt register, and a interrupt, like, flag register. So what I would do is I would say int let's just say interrupt instruction. And then a bool I don't know, is interrupt. And then this holds the instruction. And then this tells, this is a flag if there's an interrupt or not. So I guess it's kind of up to you if you want to... Actually, I guess I have to write the program. I'll have to think about it. Whether we want to have... I'll probably just throw it into the middle of some sample programs, if anything, just to make it easy. For loading and storing I/O, we're going to need to have interrupts. So you'll need to make, I guess, more memory space, like maybe another integer array for I/O. And I'll probably give you files to initialize those as well. And then we'll have int main. And then we'll just have, again, you should have a function prototype in C++, but handle interrupt. Let's just pretend this is a normal language and you can put functions wherever you want. Interrupt. Okay. So in main, we just want to have the same stuff. So before you had fetch, decode, execute. And then what we'll do is, we said last week that it's very efficient to just handle all the interrupts all at once rather than check for each individual interrupt, because that's kind of tedious. So what we'll do is we'll just, after each cycle, we'll handle the interrupt. And so every single cycle, after you're done fetching, decoding, and executing, it's very hard to simulate this because we, don't have like a full bus system, and I don't want to like throw 3 files and have you try to make it randomly come in. I'm not even sure how that would work. Yeah, we'd probably have to do multi-threading. That's a no. Not happening. I'm just going to throw it in randomly into the program. So what we'll do in handle interrupt is, again, we're just going to simulate what it was like last week. So we have an interrupt instruction register, in this case just an integer, and an interrupt flag. So we'll check, is there an interrupt? You know what? You know what would be much easier than dealing with this broken pen? I already have Notepad++ open. Let's just write this. This is way easier. Okay, so I said interrupt instruction. And we'll just save it. Sample.c. That way we have syntax highlighting too. Bool is interrupt int main fetch decode execute and you don't have to make these globals. I just suggest doing it because it's easier. Even though they tell you not to do globals, it's just as convenient in this case. Or you could create a class and do that too, if you're more object-oriented. Okay, so what it should do is checked. First, is there actually an interrupt? And I guess we'll need to initialize it to false, so there's no interrupts when we start the system. But at some point it might get set. So is there actually an interrupt? And I guess we probably want to not that. If not, do nothing. So if there's not an interrupt, we don't need to handle it, right? We can just return. Otherwise, if there is an interrupt, handle the interrupt. So what I would do is then use Decode to figure out the opcode and operand. There. So Decode, I think originally we had it do void decode, so we can just reuse the same code. I think it's easier that way. And let's discuss decode again really quick because I think some people were confused on it. Decode is going to take in, by reference, if I'm doing C++, I'm assuming we all are, int opcode int operand and int instruction. Doesn't matter what order you do these in, that's just easier for me. Makes sense to me at least. So what Decode did is we take an opcode and an operand that we assumedly have in whatever scope that we need to do it in, operation. I guess this would be operand. And instruction. So Decode, if you remember, it takes the instruction and it figures out what part of it is the opcode, what part of it is the operand. Opcode and operand from the instruction. So for example, if instruction was equal to, let's just say 10, then we know that in hex that is 00, 00, 00. And I'm going to put a space here just to make it obvious. 00, 00, 00, 00, 0A. Then this would return opcode equals 0 and operand equals A. 10. So right, all your decode function should do is separate the first byte from the last 3 bytes. And just recall the way we said we wanted to do that, the easy way to do that was opcode would equal instruction. We shift it over 24 to the right, and I guess operand then, which might be easier to do first, is equal to the instruction XOR, no, ANDed, bitwise AND, by hex 00 FFFFFF. Right, so is the user supposed to input the instructions? Yes, yeah. Although, again, I recommend reading it from my file. But you don't have to. But I recommend reading it from my file and just reading in all the integers and then doing it from that, because that way you know when you're done too. Because if you just read it straight from console, you have to figure out when the program's done. And there's no opcode for program done. But if you just read it from a file, then you know the last line is the last operation. Are we supposed to be saving this stuff to IBR, IR, MAR, like in the... Nah, I wouldn't say you should go that in depth. Just do an accumulator, honestly. I mean, if you want to, by all means. But, like, I mean, that's all hidden to the user, I guess. One's like an instruction register, MAR. Actually, yes, do the IR, but that's what the stuff I had last week was. Just I had... Actually, no. This right here that's basically the IR. I mean, it's simple enough. It doesn't have to be like one-to-one. When you're writing an emulator, you just want it to do the same stuff. You can't really expect to be perfect. And in fact, you should probably try to do it the easier way, because then it's a little more efficient as well. Class CPU with class CC and ALU. I mean, if you want to do it that way, by all means. You just have to do like one extra step. It's painful. Fair. I would just do an integer instruction. Just store it there. Don't do an IR, and then make an integer accumulator as well. I mean, do that at least. I mean, you can't really simulate it without an accumulator. Yeah, and I wouldn't go too overboard. Does everybody remember why these work? Or do you want to see an explanation again? Also, I think it's almost 12:50, so if anybody has to go, by all means go. I'm just going to keep talking, I guess, for a little bit longer. Yeah, so is everybody okay with this? Why this works? Yeah. And if not, stop me. I did talk about it last week, but just remember bitwise AND, because somebody actually asked me about this. Remember that bitwise AND is just, it takes all the bits and it ANDs them together. So like ANDing this bit string with this bit string gives me actually the same bit string. But if I had like 0, 2, it would give me 0, 0, 0, 0, 0, 0, 0, 0, A. Because when I AND something together, it expects them both to be 1. So when I AND a string together with ones, just the part that I want, anything that isn't a 1 is going to give me exactly what I had before, because 0 and 1 is 0. And if you start it with a 0, you get a 0 out. And 1 and 1 is a 1, which is exactly what you started with. But notice that like 1 and 0 is 0, which is not what you started with if you had 1 and then you AND it with a 0. Yeah, so that's why this works. How large should our cache be? Large as you want. I would say just make it, I don't know, like half the size of memory. Just don't make it too big. If I lessen the blocks and RAM for my program because my laptop... Yeah, you can. And that's actually what the... that's why I included that memory generator.py. You can change the size of what you want to generate. Make sure to have a note on my PDF. Got it. Yeah, so let's just finish the interrupts thing, unless anybody has any other questions, and then we'll just go from there. So yeah, if there's an interrupt, do something. If not, return, because there's no interrupt. You shouldn't waste your time. So handle the interrupt, and then again, we need to figure out what it is. So what I would do is I would create int. Well, we already have an interrupt instruction, right? Actually, yeah, maybe having the IR is a good idea. Yeah, somebody brought that up. Let's move this that I had in main to a global scope. So that's the IR. It's the instruction register that holds whatever instruction is being executed. So we'll handle the interrupt. It's probably already in the instruction register. We figured it out. But let's just keep these locals. So we'll say int interrupt opcode interrupt operand. So let's make locals for that. And then we'll say decode the interrupt opcode, the interrupt operand. And then now we have a global instruction, so I think that's easier. And you might not even need to put it as a parameter if that's the case. So right, we're just going to have an opcode and an operand, which is really just the same thing as up here, but it's just specifically for interrupt opcodes and interrupt operands, which is no different. If you wanted to make it a global, by all means, do it. Just trying to keep it a little realistic, I guess. So this, we know, correctly decodes it, so we can just reuse the same code from the last phase. It will store the correct opcode in here and there, and then again, really it's just the same as your execute stuff. So we decode it, and then again, I did give you opcodes for this, so you don't need anything extra. We just do a switch code statement with the opcode, and then we can do something like case load IO, load from IO at operand address, break, case store IO, store from store memory address operand at in IO. No, I'm wrong. Store load from IO at operand address on IO to accumulator, and store accumulator to memory address operand in the output device, and then break. Oh, I'm here for the record. Thank you. Yeah, I'll get the attendance. Does that make sense? Obviously, I'm not going to write this for you because that's what you're supposed to do. But you just you handle the two interrupt cases, which is I/O in this case. Are adding the IS stored in the emulated main memory when we store the computer, or are they just read from the file? You can store it in main memory if you want. I did it separate just so that it's easier. So I would read both files. Again, obviously that's not accurate to the actual emulator, but I figured it would be easier for you guys to implement if we did it that way. Just so you don't have to keep a program counter register, which, I mean, you could. Again, if you want to make it super realistic, I mean, you can change as much as you want. But if you do decide to do it that way and keep like a section of your main memory for instructions, make sure you have a way to know when you're at the end of a program, so you're going to need to keep some sort of pointer index. And then I also recommend throwing it at the end of memory, even though, again, that's not realistic, because I threw all of the testing data at the beginning of memory. All right. Any other questions, I guess, before we call it a day? Yeah, you could make this super complicated. We're just doing end of file work for end of program. Yeah, if you decide to read from my file that I gave you, that would do it. If not, you have to create an opcode specifically for that, which again is not realistic and is probably also more tedious to do for you. What is the difference between load IO and load? Load IO loads from an IO device. So let's just say I plug a flash drive into my computer. If I did load IO, it would load from the memory bank on the flash drive, get designated with some sort of identifier, some ID for the flash drive. But if I did just load, it would load from RAM. That's from what I'm seeing, it's version 2. It shouldn't be version 1. He didn't mention it in version 1, from what I read. But it's basically just the same thing. In this emulator, it's not really going to do anything different. It's just to simulate it. On an actual computer, you have those separate because you have to access a different port for input and output devices than main memory. And it's also a lot slower. Any other questions? So in execute, for cases load IO and load IO, you would just set the interrupt flat. Oh yeah, sorry. Yeah, I meant to mention that. Yeah, you're exactly right. Yeah, and you should break after every execute anyways, just because, I mean, there's no reason to keep going. Yeah, I think that's the best way to do it. Again, consider that's not realistic because we would have things running in parallel, which if we did it in C or C++, would mean that you have to open threads and then have those threads maybe just randomly throw interrupts and stuff. And that's too much. I'm not going to ask you to do that. If you want to, go crazy. But yeah, just in the load IO, set the interrupt flag. And actually, thank you for bringing that up. One other thing you should do when you finish your interrupt is interrupt equals false. Set it back to the interrupt register being false. Otherwise, you're going to keep checking it over and over again. That's something I meant to mention. Any other questions? No problem. Alright, I think everybody's good. For load IO and store IO. Oh, do you know when this will be uploaded? Like testing data? I mean, I can try to finish it today, I guess. I just have to do one thing for the school. What exactly is the IO device here? It could be anything. Oh, I mean the video? I'm going to upload it right now. It just depends whenever Jorge gets to it. Because he re-uploads it onto his YouTube channel. And the IO device could be anything. It could be like a flash drive. It could be a printer. It could be a keyboard. We're just assuming it's something random. You could all add him if you really wanted to. I mean, I'll tell him. I usually message him about it. It's just whenever he's free. But we're also working on something else today. So, I mean, I guess I'm doing more of it, but he might still have to do some stuff. All right.